If you want to understand exactly how our modern digital infrastructure is built, you really shouldn't look at the billion-dollar server farms humming away in the desert.
Right. Or those flashy Silicon Valley keynotes.
Exactly. I mean, look instead at this, like, deceptively mundane artifact from the winter of 2010. It's a digital file that weighs exactly 129 kilobytes.
Which is just remarkably small. I mean, to put that in perspective for you, a single high-resolution emoji on your smartphone.
Takes up more space.
Yeah, it requires way more data than this entire document. And yet the density of logic packed into those few kilobytes is just staggering.
It really is. And that is the mission for our deep dive today. We are extracting the hidden value from this specific, highly concentrated artifact.
So what exactly are we looking at here?
Right. So we're looking at a single course page from the Massachusetts Institute of Technology, specifically from their OpenCourseWare platform. It's the syllabus and the lecture notes for a class called Introduction to Programming in Java.
Yeah.
And we're focusing on Lecture 2, which was taught in the Electrical Engineering and Computer Science department. Okay, let's unpack this because, while it might just look like a basic list of concepts and a quick download link, this document is, it's an absolute portal.
It really is.
It's this direct blueprint of how elite institutions construct the foundational mental models of software engineering for their undergrads.
And, before we even analyze the code itself, we really need to examine the delivery mechanism because the medium is just inextricably linked to the message here.
Oh, absolutely.
The fact that you can simply navigate to this web page and pull down MIT's internal lecture notes, I mean, that represents a profound shift in how institutional knowledge is treated globally.
The scale of that platform, the OpenCourseWare platform, which is outlined right there in the source material, is just massive.
Yeah, it's huge.
We are talking about over 2,500 courses and materials freely shared with learners and educators anywhere on the planet.
Anywhere.
And it's all governed by a Creative Commons license. The copyright spans from 2001 all the way to 2026.
So that's a quarter century.
Right, a quarter century of elite academic intellectual property, just effectively open-sourced.
What's fascinating here is the ideological pivot that OpenCourseWare actually represents.
How so?
Well, for hundreds of years, the absolute bedrock of elite higher education was scarcity.
Right.
Like the value of the institution was directly tied to how many people it could keep out.
Oh, that makes total sense. You had to clear these grueling admissions hurdles.
Exactly. You pay astronomical tuition, you physically relocate to Cambridge, Massachusetts, just to see what was even on these syllabi.
Yeah.
But by publishing 2,500 courses under a Creative Commons license, MIT fundamentally decoupled the knowledge from the physical campus. They basically recognized that the logic of engineering is most valuable when it operates in an environment of total abundance.
It's an incredible shift. I mean, you're effectively being handed the master keys to one of the most restricted access intellectual vaults in the world.
Really?
But I do have to push back on the romanticism of that just a little bit.
Okay, fair enough.
Let's look at this pragmatically for a second. You and I both know that downloading a 129 kilobyte PDF is not the equivalent of actually earning an MIT degree.
Oh, definitely not.
Right. Like, does staring at the single web page actually replicate the undergraduate experience for someone who's just studying at home in their bedroom?
No, it absolutely doesn't. And I think that distinction is really crucial to make. Because when you download this PDF, you aren't downloading the physical ecosystem.
Right. You're alone.
Exactly. You don't get the late-night study groups in the dorms. You don't get the office hours with some Turing Award winner.
Yeah, or the peer pressure.
Right. The peer pressure of being surrounded by valedictorians. What you get is just the exact intellectual roadmap.
So the raw data.
Yes, the rigor of the information remains identical, but the burden of discipline shifts entirely onto you, the independent learner.
That's tough.
It is. MIT is providing the blueprint, but they're not going to force you to build the house. And that demands a level of solitary critical thinking and, well, self-motivation that is actually much harder to sustain than just sitting in a lecture hall.
That is a highly clarifying way to look at it. You get the raw materials, but the synthesis is basically your problem.
Exactly.
And speaking of the environment where these materials were originally forged, here's where it gets really interesting.
Oh, yeah. The metadata.
Right. If you look at the metadata on this course page, this was not taught during some standard leisurely fall or spring semester. The syllabus specifies this course was executed in January IAP 2010.
Right, the independent activities period.
Yeah.
If you want to understand the aggressive pacing of this specific lecture, you really have to wrap your head around the psychology of IAP.
Because from what I understand, IAP is this highly experimental, concentrated mini-term that runs right in the middle of the freezing Massachusetts winter.
Yeah, it's pretty intense.
It's effectively a 4-week sprint, right?
Precisely. It's a highly compressed academic term.
Ah.
And when you think about what that means for a subject titled Introduction to Programming in Java,
Which is for beginners.
right, a course designed to build a foundation from absolute zero, it requires a complete rewiring of a student's pedagogical approach.
Oh, I bet.
The instructors are basically forced to condense what might typically take months of gradual cognitive scaffolding into a single month. It is an absolute pressure cooker.
Which, explains another detail on this page that initially confused me.
What's that?
Well, under the instructor's heading, we see 3 separate names: Evan Jones, Adam Marcus, and Eugene Wu.
Ah, yes.
Now, if this is merely an introductory class teaching the basics of Java, why do you need a trio of instructors? I mean, in a traditional university setting, you usually just have one professor lecturing at a chalkboard for an intro class.
It's a really great observation. And the answer highlights a fundamental truth about software engineering itself.
Which is?
Writing code is not a spectator sport. You cannot learn it simply by watching someone else write it on a board.
Oh, that's a good point.
And for a beginner, learning a strongly typed language like Java is an incredibly fragile psychological process.
Because it's so strict.
Exactly. The computer has zero tolerance for ambiguity.
Right, like a single missing parenthesis or a misplaced semicolon, and the compiler just throws a fatal error and refuses to work.
Exactly. And when an 18-year-old student hits that wall, when their logic is conceptually sound, but the syntax is microscopically flawed, the frustration can cause them to just check out entirely.
Yeah, they just give up.
Right. So you don't need 3 instructors to deliver the lecture. You need 3 instructors to triage the fallout.
Oh, wow. So they're like a rapid response team.
Basically, yeah.
Yeah.
Having Evan, Adam, and Eugene in a 4-week boot camp ensures that there's this highly supported collaborative safety net. It allows the teaching team to physically walk the room, look at a student's terminal, and intervene before the cognitive overload becomes paralyzing.
That's fascinating.
It's entirely about maintaining momentum in a fundamentally unforgiving environment.
Man, that reframes the entire document for me. We aren't just looking at a list of coding concepts. We are looking at a highly curated survival guide for a 4-week intellectual sprint.
That's a great way to put it.
So let's actually open up that 129 kilobyte PDF and look at the actual grammar they were teaching to these undergrads. The syllabus kicks off Lecture 2 with types, variables, and operators.
The absolute structural foundation of memory.
Right. Now, I often hear people explain variables using fairly simplistic metaphors, like labeling a cardboard box or setting up different shaped containers in a kitchen.
Right, the Tupperware metaphor.
Yeah, exactly. But looking at the density of this MIT curriculum, that feels a bit reductive. If you're building enterprise-level software, a variable isn't just a kitchen container, right?
No, not at all.
It feels more like a rigid architectural blueprint. You are defining the exact physics of a specific zone in the computer's memory.
That is a much more accurate way to model it. It is an architectural contract. In a strongly typed language like Java, the type dictates not just what the data is, but how the machine is allowed to interact with it at a binary level.
Okay, so it's a hard rule.
Yes. If you declare an integer variable, you are structurally allocating a very specific amount of memory.
Right.
If you try to force a string of text, or even just a number with a decimal point, into that strictly defined integer space, the container doesn't just leak. The compiler refuses to build the application entirely.
It just shuts down.
Yep, it's the very first lesson in enforcing strict constraints.
But those constraints lead me to something in this syllabus that I really struggled with when I first read it.
Okay, what was that?
The next topics on the docket for Lecture 2 are division and order of operation. And I have to be honest, reading that on an MIT computer science syllabus feels kind of bizarre.
It does seem a little out of place.
Right. Like, we are talking about some of the brightest mathematical minds in the world, and they are spending an intensive January term learning parentheses, exponents, multiplication, and division.
Well, if we connect this to the bigger picture, you'll see why it's arguably the most important paradigm shift in the entire course.
Okay, I'm listening.
The teaching team is not teaching basic math. They are systematically breaking down the students' reliance on human intuition.
What do you mean by human intuition? Like how we solve problems naturally?
Yeah, exactly. Because human beings are incredibly flexible, context-aware thinkers. Like if I hand you a napkin with a hastily scribbled math equation, and maybe the division line is a bit crooked or a parenthesis is clearly implied.
My brain automatically fills in the gaps.
Right, you infer my intent. But a machine has absolutely no capacity for inference.
It only sees exactly what is typed.
Exactly, and it processes it with a ruthless, literal obedience.
Okay, give me an example.
The classic example in Java, which they undoubtedly covered under that division topic, is integer division. If you tell the computer to divide 5 by 2, but you've defined those numbers strictly as integers, meaning whole numbers, the machine doesn't understand the concept of 2.5.
Because 2.5 isn't a whole number.
Right, and it doesn't round up to 3 either. It literally truncates the decimal entirely and just hands you back a 2.
Oh, wow. Wait, really? It just chops off the 0.5?
It just chops it off. It's gone.
So if a student assumes the computer is going to do the math the way a human would do the math, their entire program is immediately compromised.
Precisely. Teaching the order of operations in code is about teaching the student that the machine's syntax overrides human logic every single time.
That sounds like a really frustrating lesson to learn.
It's a painful lesson. The computer is never wrong. It's executing exactly the sequence of commands you gave it. If the output makes no logical sense, the failure is entirely on the engineer.
That makes perfect sense. They really have to eradicate the human tendency to assume context.
Understand.
So, okay, once these students understand how to securely allocate memory with variables, and they've internalized the absolute literalism of operators and division, they are faced with a new problem.
Right, the next step.
Because static memory and basic math operations aren't particularly useful if you have to rewrite the exact same instructions over and over again.
Right, it doesn't scale.
So how do they actually make the code modular?
Which brings us directly to the second half of the Lecture 2 syllabus. Methods, parameters, return values, mathematical functions, and conditionals.
Okay.
This is the pivot from writing a script to engineering and architecture.
So what does this all mean in practice? Because when I see methods, parameters, and return values, I don't see a list of instructions anymore. I kind of see an industrial API contract.
Oh, I like that.
Yeah.
Walk us through how you visualize that.
Okay, think about a massive manufacturing plant. You have its specific machine on the assembly line. That's your method.
Okay, the method is the machine.
Right. The method is a self-contained black box that performs one highly specific, complex task. The rest of the factory doesn't need to know the internal physics of how that machine works.
They don't care how it does it.
Exactly. All the factory needs to know is the contract. If we feed this machine the correct raw materials, which are the parameters, it guarantees that it will spit out a very specific finished product.
Which is your return value.
Right, exactly.
That is an excellent framework. You're basically describing the core tenet of abstraction.
Abstraction, okay.
Because as software scales, it becomes completely impossible for a single human mind to hold all the logic at once. By bundling operations into methods, you are encapsulating complexity.
You're hiding the messy detail.
Yes. You isolate the moving parts. If something breaks, you don't have to search through a million lines of code. You just check if the inputs and outputs of that specific method are honoring the contract.
So it limits the damage.
It's entirely about containing the blast radius of potential bugs.
But a factory line that just mindlessly takes inputs and spits out outputs is still just a rigid machine.
True.
Like, it can't adapt to changing conditions. If the user does something unexpected, a static method doesn't know how to handle it.
Right.
Which brings us to what might be the most powerful concept on the syllabus: conditionals.
And this raises an important question. How do you engineer a machine to mimic human decision-making?
Yeah, how do you give it a brain?
Well, up until this point in the January boot camp, the code is entirely linear. It executes line 1, then line 2, then line 3, just marching downward without any awareness of its environment.
It's basically just a high-speed calculator.
Right. Conditionals are the mechanisms that introduce forking paths of logic. They're the if this, then that statements.
Okay.
They allow the program to evaluate a live state, like, is this variable greater than 10, or does this user have admin privileges?
And it decides what to do based on the answer.
Yes. If the evaluation resolves to true, the program dynamically routes the execution down one path. If it resolves to false, it routes it down an entirely different architectural branch.
So it's the spark of responsiveness. Without conditionals, you just have a document that does math. But with conditionals, the software can actually react to the user.
Exactly.
It can adapt to messy inputs. It actually becomes interactive.
It becomes functionally speaking, intelligent. And the fact that Evan, Adam, and Eugene were driving these students all the way from basic memory allocation to architectural abstraction and forking logic within just the second lecture of the course.
That's
It
wild.
really highlights the sheer velocity of an elite computer science curriculum.
It is a phenomenal cognitive ramp-up. So let's take a moment to review the three line we've just mapped out here.
Okay, let's do it.
We started by looking at the meta context, right? MIT OpenCourseWare breaking down the gates of institutional scarcity and sharing 2,500 courses with the world.
Huge shift.
Then we examine the intense psychological pressure cooker of a 4-week January IAP term, where 3 instructors had to basically triage the fragile process of learning strict syntax.
The rapid response team.
Exactly. And then we drilled deep into the architecture of Lecture 2 itself. How variables allocate rigid memory, how operators enforce the machine's unyielding literalism.
Chopping off that 0.5.
Right, chopping off the decimal, and how methods and conditionals allow engineers to build abstract, reactive systems.
It is the absolute bedrock. I
Oh.
mean, whether you are building a simple mobile application or architecting the machine learning algorithms of the future, they all ultimately compile down to these exact foundational concepts.
Which is what makes this tiny 129 kilobyte PDF an incredibly potent artifact for you to understand, whether you manage software teams, build products, or, simply interact with the digital world every single day.
Absolutely.
But before we sign off, there is one final, easily overlooked detail buried at the very bottom of the OpenCourseWare page that I know you wanted to highlight.
Yes, I'm glad you brought that up. Right at the bottom of the source material, there is just a standard legal exit disclaimer.
Okay.
If you click an external link, a warning pops up that reads, "You are leaving MIT OpenCourseWare. Please be advised that external sites may have terms and conditions. MIT OCW is not responsible for any content on third-party sites."
I mean, it just reads like standard institutional boilerplate to avoid liability. Like, hey, don't sue us.
Right. On a literal level, it is exactly that. But conceptually, I think it serves as the ultimate metaphor for software engineering itself.
Oh, interesting. How so?
Well, think about the progression of this lecture. A university syllabus, a downloaded PDF, or the local development environment on your laptop. These are safe, controlled academic sandboxes.
Right.
You can declare your variables, enforce your order of operations, and test your conditionals in an entirely closed system where the logic behaves exactly as you dictate.
The environment is perfectly sterile. Nothing unexpected is going to happen.
But the moment you deploy that software out into the real world, the moment it interacts with live users, conflicting databases, and unpredictable network latency, you are leaving the sandbox.
Oh, man.
MIT is no longer responsible. The training wheels are off. The real world is the ultimate third-party site, and it emphatically does not play by the clean, sterile rules of an undergraduate syllabus.
Wow.
The true test of an engineer isn't whether their code works in the lab. It's whether their abstractions and conditionals can survive contact with the chaos of the external world.
You are leaving the sandbox. That is a brilliantly provocative way to look at deployment. You can master the strict grammar of the machine, but you still have to engineer for the unpredictability of reality.
Precisely.
It truly is amazing how a tiny digital syllabus from 2010 can hold the entire blueprint for how we navigate the modern digital infrastructure. Thank you so much for bringing this artifact to the table and breaking down the pedagogy with such depth.
It was my pleasure.
And to you, listening right now, thank you for diving into the weeds with us. Keep examining the unseen architecture of the tools you use every day. Keep pushing past the basics, and we will catch you on the next deep dive.